Good afternoon, everyone. Welcome to today's AI4OPT seminar. So today we have Anchi Wu. Anchi is an assistant professor in the School of Computational Science and Engineering at Georgia Tech. Before this, she was a postdoctoral researcher at Second Mind, Brain and Behavior Institute at Columbia University. She received her PhD from Princeton University in computational and quantitative neuroscience. She has been recognized as a rising star in EECS as a DARPA riser and also a Sloan Fellow. She is interested in developing various statistical models to characterize structure in neural and behavioral data. And today she is going to tell us about improving variational inference. So welcome, Anchi.
Thank you for your intro and for having me in this seminar. I'd like to talk about some work that has been done and ongoing in the lab. This talk is mainly about different kind of variation inference problem existing in these complex probabilistic modeling. So just a quick, how many people have already known variational inference well? Yeah, because that's going to be like the base knowledge we want to build on. So first, briefly, I want to introduce what is variational inference. Generally, in probabilistic machine learning, people try to solve problems when they have some observed data X and some hidden variable Z. Like for example, hidden Markov model, right? You see observed sequence X and you want to infer hidden state Z. So that's what the goal is, right? You want to solve the problem doing inference to learn this unknown posterior PZ given X. And generally, if you're lucky, if your model is very simple, you can even get this PZ given X by doing this division, right? You get the joint distribution PZ given X and divide it by the marginal PX. But unfortunately, for most of the interesting models, you don't have very simple and naive models. So the problem is the denominator cannot be calculated in an explicit form. It's not tractable. So in which case we cannot get the exact posterior representation. And what people are going to do, people appeal to approximate posterior inference. Approximate posterior inference try to learn what's the posterior PZ given X, but in an approximate way. So that's what the variational inference can help for. Variational inference turns this posterior inference into an optimization problem. Concretely, what people do is, instead of learning the explicit PZ given X, we assume there exists a variational approximate family, a variational family of distributions QZ given V. V is the unknown parameter, right? Parameterize this Q distribution. They want to learn V, and so the circle kind of define the whole family, so that the QZ given this V value would be very close to the true posterior. And the way they achieve this closeness is by minimizing the Cal divergence between Q and P. Any question?
Some question I was trying to understand, given that we don't know what the Z of given X is, how do we compute the distance between?
Yeah, a perfect question leading to the next slide. But let's say, we don't know that. That's the thing people do. People try to solve. But the high level thing is you construct this Cal divergence to minimize the Q function, actually minimize the objective with respect to the V value, the parameters you Q. Okay, so that makes sense. That's what the variational inference is trying to solve.
Can you give a concrete example of, say, what X can correspond to in practice, what the Z would be?
Sure. For example, in so for example, in a linear dynamic system where your X would be your kind of sequence of observation, and Z can be a continuous latent dynamics. Like the easiest case would be quantum filter when everything is Gaussian, but that's too simple again. Let's say your X is discrete values, which actually in neuroscience people do a lot. Like X would be the spiking events of neurons, and Z would be some continuous distribution evolving with a linear dynamics.
And so in practice, I should be able to observe X
You observe X, but you
And
don't know.
Z, I cannot observe it.
Yeah, you don't. Because you only see the discrete values, you don't see the continuous dynamics underlying that. So that would be a very simple and very commonly studied hidden variable model or latent variable model in neuroscience. But I guess people in other fields would also face similar issues.
Okay. But then I still want to sample Z.
Sorry?
I still want to sample Z.
The goal is to learn the posterior, given the observation X, what's the hidden state, what's the latent variable, what's the posterior of the latent variables. That's what we want to learn. But you cannot easily learn by just dividing the joint by the marginal because you don't know the marginal. So we have to use some approximate inference to learn PZ given X. The way you do that is you want to learn some Q that approximate that PZ by minimizing the KL divergence. So in an ideal case, your family is broad enough that you cover P, so your KL will become 0.
So the math I understand. The one last thing that I don't fully understand is, so I observe some data X.
Right.
There's some latent variable that I cannot observe directly.
Right.
And I'm trying to model the conditional distribution or the joint distribution between these latent variables and the one that I can observe, right?
Right.
But then if I cannot observe Z in practice, how do I know that I actually have a
Yeah, that's the same question as I'm diving into that right now.
Okay.
But to motivate, like people want to minimize KL divergence. Okay, the same question, we don't know PZ yet given X. We can know QZ given X, right? You can just parameterize with a Gaussian, for example, you just learn a mean and variance, but what is PZ given X? So here's the trick people do. Okay, let's say we want to minimize KL divergence, which is the Q and the distance between Q and P. Okay, the trick is you want to rewrite this KL divergence into this. It consists of 3 terms. The first term is the expectation of the log P given X. This is people call data, conditional data likelihood. So it's a conditional distribution for the data, right? Get condition on arbitrary Z, what's the likelihood of X? That's people usually know, like in hidden Markov model, that's going to be the emission probability. And Q is something you know, so the first expectation term, you can calculate that. The second term is the KL divergence between Q and the prior. Prior is something you can know. That is, that's a Gaussian or that's a Bernoulli. So that's something you know. And the last term is a log P, which is the main hurdle. But the lucky thing is a constant term with respect to the parameter D in Q distribution. So people just drop the last term and try to optimize the first 2 terms. And that's what people call ELBO, the evidence lower bound. So equivalently, instead of minimizing KL between Q and the true posterior, we are maximizing the ELBO. The ELBO consists of 2 terms. The first term is the expectation of the log data, and the second term is the KL divergence between the Q and some prior assumption. So we'll explain more about these 2 terms using the Bayesian neural network as an example. But this is kind of a standard ELBO people talk about in variational inference. And we seem to get to some tractable objective function, right? Because the original one is intractable. But still actually calculating this expectation and also the KL divergence can be non-trivial in many cases, especially when you have complicated probabilistic model. When I say complicated, it's like not everything is Gaussian, right? You can have very complicated dependence, graphic models. So that's really where the naive like variational inference with ELBO can have issues. Any question after this point?
Which part do you think in ELBO is the most intractable one?
Most likely it's the first term, but we actually also going to show the second term could be an issue. But because the first term is what? Is an integral of log P multiplied a Q distribution. If log P is a very difficult distribution, how you can assume the whole expression can be solved, right? The integral can be solved in analytical form. So most likely you don't.
In most problems, we assume that we have some sort of a likelihood term that will give us the probability of X given Z.
Right.
Okay.
So we'll get to that for the neural network case, but hopefully you can have very vague intuition up to this point. But I will convince you why that's different. Okay, so I outlined 2 different modeling problems. One is Bayesian neural network, one is partially observed multivariate hockey. But I actually want to make it slow since this is more like student audience and want to make sure people all understand the details. So we'll see where we can approach to given the time limits. Okay, maybe let's just start from the first one. Okay, so first I'm gonna talk about Bayesian neural network. To compare, right? People are familiar with the standard deterministic neural network, where you just have some deterministic input, deterministic parameter W, and then generate Y in a deterministic way. So the good thing about neural networks, you can get a very flexible class of models because you can change the layers, can change the number of hidden nodes or the nonlinear activation function. But there are some drawbacks of deterministic model, right? Because you cannot really easily handle uncertainty, cannot easily impose some regularization over the weight. But there can be a broader class of regularization which help with the generalization. So that's what Bayesian neural network can do. It inherits the benefits of flexible models, but also impose the prior assumption over the weight. Right now, the weight are not just determinant values. You can think of their random variables sample from distributions. This kind of model can handle uncertainty or regularization better. So that's Bayesian neural network. And in Bayesian neural network, what's the goal? People observe X, people observe Y, but people don't know W, right? We still want to infer W, but not just doing back propagation. You're not doing posterior inference because W now are random variables from some prior assumptions. So the goal is to infer the posterior of W given X and Y. And hopefully, although it's not super obvious, but the thing is still, right, the PW given XY is PWXY joint divided by the marginal PXY, but what's the marginal, right? So obviously it's an intractable term. Then back to the variational inference, you can come up with a Q distribution. Here we parameterize by theta. Usually the parameter, the notation people use. You want to learn the Q theta W that approximate your Q posterior in an accurate way. Then back to the initial motivation, right? You cannot solve it by minimizing the scale divergence between them, so you optimize the ELBO. Okay. And the ELBO consists of the two terms, the same as the previous slide. And here you can see Y is so generally what people do is you have X and you have W. You multiply this. So basically these two parts propagate through the whole neural network and generate a mean and variance for Y, right? And now even to integral over such a log P term for W, how you can do that? It's impossible, right? Because W is entangled with X in all these layers. So there's no way you can solve this log term, multiply the Q integral, right? And the second term is actually here, if you're familiar with, I guess you guys most of familiar with optimization, you want some regularization term to penalize your weights. So the first term is for feeding the data, like the loss function for the data feeding, and the second term functions more like the regularization parts. But these two terms actually have both issues in Bayesian neural network context. And we want to address these two issues to improve the variational inference for Bayesian neural network generally. Any question up to this point? Question?
So like speaking about the first term, like in practical, can we use some like empirical information?
Yeah, that nicely leads to the next slide. I like all those questions. They're all like very good questions. Yeah, exactly, right? When you see intractable integral, what people do use Monte Carlo, right? Use empirical method to get some Monte Carlo estimator. So to solve the first part, people use Monte Carlo sampling. The idea is basically this, right? You have a distribution over W, you sample W from the distribution, propagate that through the network to generate a sample of Y, right? And then if you do this multiple times, you will get a distribution of Y. So basically, you are propagating the whole distribution of W or the uncertainty in this distribution through the neural network to generate the uncertainty in the output distribution. That's the Monte Carlo sampling idea. But the main problem is the gradient variance is very large, right? Because you're using the Monte Carlo sampling to approximate the gradient as well. And the gradient can be very, noisy, especially when you only have a small number of samples. So here's a figure to show using MC-based variational inference. When you have very small number of samples, the variance can be huge. Usually people increase the number of samples, which make the variance shrink, but that's still a non-trivial number. Question.
The number of samples, is that the number of data samples or is this samples from W?
Oh, that's the sample for the approximation of the integral. So it's like Monte Carlo. We're not doing stochastic batch optimization, like not sample from the data. It's sample
For W.
Sample W from the Q distribution.
Okay.
Like you're learning Q, which means every time you get a new Q, you have to redo the sampling. So that's a lot of sampling. So there are existing works try to reduce such gradient variance, not surprisingly. And our goal is to, can we do a deterministic method? Instead of doing sampling, can we get a deterministic approximation for the expectation term, which will completely eliminate the gradient variance? So that's the motivation. Okay, before I dive into the deterministic, I want to go through the Monte Carlo approximation with the neural network example. Remember, the expectation term, we can use a Monte Carlo empirical estimator, which is as active number of samples of W from the Q distribution. And based on the sample Q, based on sample W, you can just assume these are like deterministic network and just propagate this X through each sample of W, right, to generate the sample of Y, which can be used to calculate the summation. And concretely, at the first layer, you have a deterministic X input. You get a bunch of sample of W, multiply them to generate the sample of A0. And then you do the same thing for layer 1, layer 2, all the way to last layer. You will get a bunch of sample for AL. And then you use this AL sample to generate a sample for Y, which is used to calculate the expectation term. Question? Make sense? Okay. So basically, MC method is propagating the uncertainty via samples, right? So then question is, can we deterministically propagate an entire distribution rather than just propagating the samples? Ultimately, the goal is to get the distribution in output side. And can we do that really with a deterministic form? So our goal is to come up with some function for each layer, so that for each layer, if I know the input distribution A0, I know the distribution of W0, can we give you back the distribution of the output A1? So that's the goal of the function, right? If let's say we know these two, and then we know this function, then we can get this. If we know this, then we can propagate the distribution to the last layer. And fortunately, we can assume this A1 distribution to be Gaussian. Although that sounds like very harsh assumption, but here's why. We know A1 is a linear multiplication of W and H, right? So H passed through the nonlinearity, for example, ReLU or stepping function. And then you multiply H with W to get A1. And if W and H are both IID samples, and the number of hidden units in that layer is large, then according to central limit theorem, A1 would be Gaussian. Right? So that's kind of the intuition. Then all we need to do is to learn what's the mean and variance expression of this A1 layer. Okay? A very simple illustrative example is, let's say A1 has 2 dimensions. And then W is a 2D Gaussian, H is a truncated Gaussian if we have a Heaviside layer, like Heaviside function or a stepping function. Then, if we have only one hidden node between WH, it definitely not look like Gaussian. But if you increase the number of hidden nodes in the layer, you will have something looking like the Gaussian. So that's kind of the motivation. And generally, in practice, you don't really need 1,000, 10,000 hidden nodes. 300-ish is a reasonable number to give you something Gaussian. Yeah. Then, okay, hopefully I convince you that A should be Gaussian. Then what's the mean and variance, or what's the mean and covariance expression of A? Basically, question.
By 300, you mean the width of the network?
Right, right. I mean, yeah, of course, your dimensionality cannot be too, how to say, it depends on your input dimension, right? If your input is like 10,000 by 10,000 image or whatever, that's definitely more. But yeah, I mean, in this particular work, we haven't like deal with images or super high dimensional input. So we actually work with 300 to 500-ish hidden units. But if you use high dimensional data, you might want to increase that. But we actually later going to show it's actually the complexity is linear in the number of hidden nodes. So it's not too prohibitive if you have even very, very large data.
And when you get close to the end of your network, or if your network is like a quarter structure, when you get closer to the, towards the end of your network, then the number of nodes will decrease. So is the assumption still valid?
We don't really decrease that. Generally, we want everything to be as wide as possible. Yeah.
I have a question. This contradicts my intuition about the representation power of neural network. It seems that you're saying that after a couple of layers, things are still normally distributed. But we know that neural networks seem to be able to capture a variety of different shapes of data. Things are not normal. So how do you reconcile the two?
So it's not the whole layer is Gaussian. Each unit is Gaussian. So each unit is IID Gaussian from the other. It's not really exactly IID, but they might have some fundamental correlation. So for example, if output is an image, you can assume each pixel is a Gaussian. So we model each unit independently, like basically by propagating information. It's not like the whole output should follow a giant unimodal Gaussian distribution.
Okay. All right.
So basically to calculate the mean and variance of A, actually, if you do a bit of math, you can see you just need the moments from H. So you need to calculate the first order and second order moments from H. And for some function like stepping function or revolve function, the mean has some closed form expression. If you do the integral, right? It's all like, right now we kind of convert the whole Bayesian like Variational Inference problem down to this very particular like math integral derivation problem. But the bad thing is the second order moments usually don't have a nice closed form expression. So we can visualize the function and visualize the moments and see what it looks like. For a 2D case, it will look like something like what I'm showing here. But again, we don't have a closed form expression. We cannot write on this. If we can write on this, then we can write on closed form for A, and then everything will be deterministic, which sounds like a very trivial task. So the main difficulty really relies on how to approximate the second order moments with some accurate deterministic approximation. You have a question? No.
I have a question. H are truncated normal, right?
Right.
And HI, HHJ can have non-trivial correlation structure that you don't know, but they are joint normal truncated.
Right.
Okay.
It's, I mean, like up to this point, everything just become math. You can even forget what the distribution should look like. You can just write down, for example, the first order derivative is F is the nonlinearity, right? It's phi is the Gaussian.
Okay.
So the input is Gaussian, but the variable is password nonlinear, and then you take an integral. Okay. That'll be hard. Okay, I don't want to get to the detail how we derive that, but high level idea is we actually find some analytical expression, which is in yellow, to approximate that intractable integral for the second order moments. And we can show that that integral actually asymptotically close to the analytical form with a small residual, which is actually a unimodal residual. And we further use another Gaussian to approximate that unimodal residual, which will get a very even smaller scale residual that left in the blue in the third line. So basically the high level idea is we find two steps of deterministic function that approximate the intractable second order moments, but leaving a very small residual. And we show empirically that this very small residual doesn't matter too much, right, in terms of propagating the distributions.
I'm confused. If things are truncated normal, you should be able to use something like quasi Monte Carlo to quickly calculate, estimate their moments, right?
No, we don't do Monte Carlo, anything. So actually, again, like what I'm saying, all we deal with is the integral problem right now.
Yeah, I'm just saying
Right.
quasi Monte Carlo. Now, the quasi Monte Carlo do not have the Monte Carlo noise, right? You're just trying to approximate something second moment with some truncated normal. So I guess what I'm missing is what's the distribution of HI and HJ? Joy distribution. Do you
For the
know?
heavy set, it's going to be truncate normal, but we also deal with ReLU and with tangent with some other nonlinearity. So this is a general framework, not just for truncate normal. There's a mass derivation of what the yellow curves should look like for different nonlinear activation. But yeah, okay. But empirically, the implementation is just a couple of lines of code. It's very, very simple. There's no like sampling for Monte Carlo approximation, no noise, like that. And we do the same thing for ReLU as well. Okay, yeah, so I don't want to get into any details, but the high level idea is we can find some beautiful math expression to give you pretty accurate approximation with small enough residual. So that you can get kind of a accurate distribution outline in output layer. So here's a very simple empirical verification. We have this 2-layer neural network. The output layer has 2 nodes, M and L. M capture the mean of the data, and L capture the variance of the data. Right? That's what we. So we have a Bayesian neural network. We not only put uncertainty over the weight, but we also want the output to capture the uncertainty in the data as well. So we can show before training, before we do anything, just an arbitrary prior assumption over the weight, and we propagate this weight through the neural network using MC method and using our deterministic method. We can see the red curve, which is our deterministic function, approximate the histogram pretty well, right? Which is from the MC. And after the training, the approximation is also pretty good. So this basic thing at any stage of the training, using the deterministic approximation can well approximate the histogram from the MC sample. Which means you can basically use this method to do optimization.
Slightly confused. You mentioned that L referred to the variance,
Right.
but then I see negative values on the graph.
Oh, it's actually log. So we exponentiate that to get the really uncertainty. Question?
Like where is your W?
Oh, W is hidden in this layer. I'm not showing them.
Oh, W is inputting this.
Okay, so W, so X map to H through a nonlinear function, and H multiply W to get A. Okay, so we propose a method to solve the gradient issue, gradient variance issue for the expectation term. And there's one more thing we want to deal with is actually the prior part. As a question.
To clarify. So for each theta, you need to run this deterministic propagation. Is that right?
Right, it's like you're doing optimization, you optimize over theta. Every time you do a gradient, you get a new theta, get a new Q, and you propagate to generate the loss function. So that's exactly the same as Monte Carlo method, but Monte Carlo you need to use multiple samples to approximate, and we don't do that. Okay, so the prior part is again is a regularization term. So regularization means what? You need to do a hyperparameter selection, right? So the hyperparameter in this case is actually the prior variance. If PW is just a Gaussian distribution with 0 mean and variance S, for example, then you need to learn what is the optimal S that give you the best generalization performance using a validation set. So here is the Bayesian neural network applied to the UCI data sets. Here we show 9 UCI data sets. The x-axis for each data set is the different value of the prior variance. You can see when you change the prior variance, the likelihood value would be changing a lot. It's not a very robust, like, how to say, like, it's not really insensitive to the prior variance choice. So Of course, the straightforward method would be doing cross-validation, right? You do hyperparameter selection, but you're gonna do that for a lot of times. I mean, I think cross-validation is generally not the most efficient way to learn a robust hyperparameter. And we propose to use empirical Bayes, which will offer a lot of benefits compared with cross-validation. So the idea is W is from a Gaussian with zero mean S variance. So usually S is deterministic value you predefine. But here we put another prior over S, assuming S is a random variable as well. And generally a prior for the variance would be inverse gamma, and with a shape alpha and scale beta. Okay, so we just put an additional prior, and usually in a fully Bayesian framework, people do sampling. Like because you put a hyperprior over the parameter in the prior. But we propose to use empirical Bayes, which is basically optimize the ELBO now with respect to S. So let's assume theta is given. Given an arbitrary theta, we maximize ELBO with respect to S. But the good thing about these two priors are because Gaussian and inverse gamma are conjugate distributions. So you actually get a closed form expression of S star given as a function of the theta parameter. So given an arbitrary theta, you can get a closed form S. And if you change theta, the closed form S will change together. Then the beautiful thing is you can bring this S back to the ELBO, but now S is not a predefined fixed number, it's a function of theta. So now optimizing this ELBO would be also implicitly optimizing your S value. Okay, so that's the empirical Bayes part. And this method or this trick is actually generalizable in, I'm not sure, maybe most likely with the neural network structure, but you can use this in like variational autoencoder. We actually tried this for variational autoencoder, which also works pretty well.
How do you set your alpha and beta?
Oh, that's predefined. Okay. But usually, like in Bayesian framework, you have hyperprior for priors, and the more hyperprior you put, the less sensitive it will be to the hyperparameters. And we show the same application to the same data sets. The blue bar is the empirical Bayes. We don't do tuning, we don't do anything, we just replace S with that function, and it will learn a constant S for us. And compare with all the non-empirical Bayes method, the empirical Bayes is kind of most likely outperform all the choices that we iterate through on the grade of S. So that's the empirical Bayes result. And a question regarding this part. I think, yeah. Okay, so cool. Now we kind of solved both problems with Bayesian neural network, and we propose this deterministic variational inference plus the empirical Bayes, and we compare with some alternative methods, and we show like on these 9 UCI data sets, the test log likelihood has been pretty good generally. So the second column is deterministic plus fixed, but the fixed is the best fixed. We actually don't do cross-validation. We just run over all the possible S value and pick the best one. So it's actually a not fair comparison per se. Cool, so that's the wrap up of this part of the talk. We basically try to resolve 2 challenges. The first one is proposing this deterministic variational inference that can get rid of the gradient variance that is usually result in Monte Carlo inference methods. And we have this empirical Bayes to require no tuning, basically, for the prior variance. But the inference, the implementation itself is very efficient. We don't do sampling, we have closed form expression, which can be implemented in several lines of code. Yeah, any questions so far with respect to this part? Question?
Maybe I missed it, but what is P theta W? Is it Gaussian?
What P theta?
Like
PW is Gaussian with zero mean and S variance, and that's S is something we usually want to tune.
That's a prior.
That's prior.
But what about the variational?
Oh, for the variational, you don't put prior. So W is the latent here right now. We want to learn PW given data. and we approximate that PW given data by a QW distribution parameterized by some deterministic parameters. So we don't put a prior over the parameter in the Q function.
Yeah, so what is the form of the QW?
Oh, in this Bayesian neural network is just Gaussian.
Gaussian.
Yeah.
So we just need to like parameterize the mean and the variance
Right.
of the Q.
Yeah.
Okay.
Yeah, but if you're familiar with amortized learning, people would, instead of parameterize the mean and Q and the covariance as free parameter, you will assume the Q distribution depends on the data as well, the X. And you input X into an encoder or the amortized neural network, and you actually parameterize the network. The network parameter will be your parameter. So, I mean, that's something a bit off the topic if you're familiar with amortized learning. But if you're not, then the theta will be the mean and variance of that Q distribution. Okay, any question up to this point? Okay. Yeah. So next, I'm gonna also talk about variational inference for a different published modeling, which is partially observed hockey process. I'm not sure we're gonna have time to go through everything, but I'll try to cover as much as possible. So firstly, what is POMHP? So hockey process is a self-exciting point process people use, especially in neuroscience, to model the spiking events of single neuron. So if you have single neuron, it will have a sequence of discrete events. And people use hockey process to model the single neuron spiking events. Then people use multivariate hockey, because in multivariate hockey, you're not just, a event is not just exciting its own future, but also exciting the other neuron's future. So now you introduce this interaction or influence between neurons, which is interesting, because if you fit a multivariate hockey to a bunch of neurons spiking events, then you will end up with a neuron's connectivity matrix. And this connecting matrix will tell you how one neuron excites or inhibits the other neurons. I mean, although we're talking about hockey, but generally people can have self-inhibition in hockey process as well. So basically the benefit of using MHP is you can learn the interaction matrix between neurons. I mean, also for other application cases as well. And then we extend to the partially observed, because we might assume some events are not observed, right? Likely in neuroscience, you don't collect all the neurons that are interacting with each other. Due to the limitation of the recording, you might have some neurons that you cannot touch or don't see. So easily you will get a bunch of hidden events, but these hidden events are really interacting with the other neurons as well. So that's why we care about the POMHP in neuroscience, but as I mentioned, they might find its own application in finance, social network, a lot of different applications. Question?
Is it similar to a graph neural network, the Hawkins process, the multivariate Hawkins process?
It's not graph neural network. No, I think graph neural network mainly focused on building the graph and learn how message passing. I mean, there's connections, but I wouldn't say that's the same thing, because especially in hockey process, there is a lot of emphasis on dependence on the history events and on like there's a time dimension there. Maybe there's a time version of graph neural network, but generally you can use graph method to study the interaction or connectivity matrix. The cool thing is they deal with point process. Is a continual time step, which is probably different from some neural network, graph neural network models. Okay, so hopefully you have a rough ideas to know what is POMHP, and obviously that would be an interesting probabilistic model with very complex dependency. And again, we have observed data, which is from these observed neurons X, and we have some hidden neurons events, which is denoted as Z. And here, we're also interested in inferring what's the Z distribution, but more interestingly, we actually want to know the model parameter theta, which tell us this connectivity information. And straightforward thing people do is you can maximize the marginal px given theta by doing MLE, but obviously you cannot easily derive the marginal as we motivated early. And how are we going to do that? People will resort to variational inference. Here, actually, I want to derive the same elbow, but from a slightly different perspective, which I think is very kind of interesting. So previously we show, oh, how are we going to derive elbow? We want to minimize the Cal divergence between the Q distribution and the true posterior, right? But here we can start from a different perspective. Let's say we want to maximize the log marginal, but we don't know the log marginal. How are we going to do that? We can rewrite the log marginal into these two forms, right? So integral over the joint, and then you can introduce an arbitrary Q distribution and divide it by Q and multiply Q, right? That's just a standard trick people do. And based on the Jensen's equality, you can rewrite this log integral into the integral of the log. So now you actually derive a tight lower bound of the log marginal. And then you do one more step rewriting, you will get the same elbow. Right? Which is the first term is the data likelihood part, the second term is the prior regularization. And the difference between the original log marginal and the elbow is actually the Cal divergence between Q and true posterior. So that's another way of deriving elbow using the Jensen inequality. Any question? Okay, cool. So like I say, we want to maximize the log marginal with respect to theta, because theta is really what we care about. We can't do that, we can maximize the lower bound. Okay. But since we introduced this Q distribution, we might also want to optimize the optimal parameter for the Q distribution as well. However, applying VI for the POMHP, there are two more challenges. The first one is elbow doesn't always give you the good parameter estimation or the tightest of lower bound, especially for very complicated modeling like in POMHP and MHP. I will explain this in more detail later, but just to give you a sense like what's the graphical model of POMHP might look like. Another thing is the Q distribution, right? The choice of Q distribution is non-trivial. Previously in the BNN case, we just assumed Q to be Gaussian. Sounds like super simple, but here Q cannot be Gaussian because Q is a distribution over a sequence of Z. And we cannot assume, well, yeah, so there's certainly a lot of dependence there, so they cannot be just Gaussian. And previous choice, people assume Q to be another multivariate hockey process, but they only consider dependence between visible to hidden neurons or amount like hidden neurons, like hidden history to the hidden future. We argue that there are two major drawbacks. The first one is the inference is going to be very slow. And the second one is the mean actually some essential influence in a backward way. I'll explain this later. But here are the two challenges mainly exist to prevent us to have a very effective VI to solve the POMHP model. So the first question is, how can we get a tighter bound rather than elbow, right? If the log marginal is there, we know that elbow is actually down here, and we want to work with a better bound that actually converges to log marginal asymptotically. So that's the goal of the first part. So, okay, so let's relook at the elbow equation. Hopefully it's already been very impressive, like already embedded in your mind. It's the expectation minus Cal divergence. But generally, when Q distribution is very complicated, you don't even have a closed form Cal. Like for both the expectation and Cal term, you cannot use any closed form expression to write down. So the best thing you can do is use Monte Carlo approximator, right? You do samples from Q distribution and calculating the expectation term using the samples. Let's denote the number of samples to be K. Okay, and then we denote this to be the empirical estimator of elbow to be elbow hat. And I think it should be straightforward that elbow hat is an unbiased estimator of elbow, because if K is infinite, that expectation of elbow hat with respect to Q will be equal to elbow. Therefore, it's a down-biased estimator of the log marginal. So you can see this is the relative relationship between these. So these two will be the same, but they're all below the log P. Make sense? And the gap between them, I will actually show you the next two slides, will be the Cal divergence between the true Q and the posterior Q, posterior. Okay, So how are we gonna find a tighter bound? A general approach people use is importance sampling, which is another approximate inference method. It's a different thing from variational inference. It's a sampling based method. But the goal is to approximate the log marginal as well. And the way people do that is they want to estimate the marginal with some proposal distribution by doing the following thing. Okay, so P marginal is the integral of the joint, which is the joint over Q multiplied Q, right? This is the same thing we derive for the ELBO. Now, based on the importance sampling, what you can do is sample Z from the Q distribution, and then calculate the fraction term based on the samples. Right, so this is a standard trick people do for Monte Carlo approximation of some integral. Right. Let's denote the last term to be p hat. Right, that's the empirical estimator of the marginal, and we can tell that this marginal, this empirical estimator of marginal p hat is going to be an unbiased estimate. Right, hopefully that's also obvious. Which means p hat is unbiased. What about log p hat? Right, log p hat, the expectation of log p hat is the lower bound of log expectation due to the Jensen inequality, which is log p hat, which is log p. So log p hat is actually a down-biased estimator of log p. That makes sense? But the question is, where is log p hat compared with ELBO hat, right? Actually, it's up there. Right? It's actually a tighter bound. So in the next slide, I'm going to show why it's tighter bound. But any question regarding the importance sampling and regarding the two empirical estimators? Okay. So let's see why we have this relative position. What's the bias or what's the gap of this ELBO hat? The way to derive the bias will take the expectation of ELBO hat minus log p, which is going to be the minus of the KL divergence. Right? So that's what people have already, you probably learned this from your first machine learning class. And then what's the bias of the log p hat? It's actually minus chi-square divergence. So this is derived by previous paper already. This exists for a while. And by looking at this bound, you can tell when K is actually, the bound actually depends, sorry, the gap, the bias actually depends on K, which means you have infinite K, the gap will converge to 0. So that's why we claim it's actually a symptomatically tighter bound. Because when K is equal to 1, log p hat is equal to ELBO hat. But when K increases, log p hat will converge to log p rather than being like always down here, right? So that's why log p hat is a better, tighter bound compared with ELBO. Question?
Would the tightness also depend on the number of samples K?
Right, yeah, as mentioned, when K is equal to 1, so actually I'm going to show that in the next slide with some simulation results, but when K is equal to 1, this bound is exactly the same as this bound. But when K increases, ELBO hat will converge to ELBO, and log p hat will converge to log p. And ELBO is always below log p when Q doesn't fully match the p distribution, the posterior distribution.
And do you also have analysis on like the rates of convergence for you?
Oh, that's not done by me. That's like people pretty previous have already done analysis. Yeah, I'm not sure there's a convergence rate analysis on that perspective. Yeah, I don't do theoretical optimization or anything. So, yeah.
I have two questions
Okay,
on this. First is you only talk about the mean, but if you use it as for optimization, you have to look at variance stability of that.
Right.
Maybe ELBO hat is more stable than log p hat because importance sampling, if you have larger weight, because it gets screwed.
Yeah, first, all I'm saying is you cannot calculate ELBO. You have to use the empirical estimator.
Yes.
So, and for both the for both the ELBO and this, they have large variance.
Yeah.
But the good thing is this they all like operate in some log space, which means the variance is not like in the exponential space.
Yeah, I'm just saying, both are approximators. Not only you need to look at the expectation, as you also need to look at, like previously, you need to look at Monte Carlo noise, right? both have Monte Carlo noise. It's just one use like variability about weight. The other one maybe use Monte Carlo noise. I'm not exactly sure, but I think there's another aspect of the variability of those log p hat and elbow hat that's somehow worth an investigation.
Right.
A second question is, I don't get why the elbow being lower than the log p to be concerning. We already know it's different by a constant, right? If you're only looking at finding the best variational approximation, then different by a constant shouldn't matter. Like log p minus the elbow is a constant.
It's not a constant.
It's
It is
not?
a Q divergence between P and Q. It's not a constant. That's something actually we try to minimize.
Oh, okay. Yeah, okay, I misunderstand that part. All right, next.
Yeah, to answer your first question, there is a variability, like a variance issue. But first, actually, when you deal with very difficult problem like POMHP, you need to deal with the mean problem, right? You need to make sure the mean works, then you shrink the variance. The mean doesn't even work with elbow.
I see.
So, I mean, in the Bayesian case, in the Bayesian neural network, in the first part, the mean actually works okay.
Okay.
And now people focus on shrinking the variance.
Yeah.
But the first goal right now is actually to deal with the mean. And the variance is acceptable given that it's in the log space. Okay, anyway, we propose this new approximate inference where to learn the model parameters data, we want to maximize the log p, which is the same as important sampling. The only trick is when you choose the proposal distribution, we don't predefine proposal or we don't use variational inference by minimizing the KL divergence to learn the Q. We're actually minimizing the chi-square divergence to learn the Q. All because of the bound analysis. So this is something I want to show actually. Empirically, we can show the curve, the trend, like the asymptotic tidal bound. So here we just design very simple numerical problems where we know the log p and we know the elbow, right? We can calculate the mean closed form. And again, Q is not a perfect match of the posterior, so there's a gap there. Right? You never reach the bound. If we perform the empirical elbow hat estimator, when K takes only one sample up to 5 samples, you can see the variance of the empirical estimator shrinks, right? Which is not surprising. But the mean actually start to converge to elbow because that's an unbiased estimator of elbow, not log p hats. But if you do the same thing for log p hats, which is the empirical estimator for important sampling, you have large variance at the beginning, and when K is equal to 1, they're the same empirical estimator as mentioned, but they start to converge to log p. So as you have more samples, your log p hat will be an asymptotically estimator of the original log marginal, rather than the elbow. That means you don't need to choose a perfect Q, right? Elbow, you need a perfect Q to delete this, to eliminate this gap. But for log p, you don't need to have a harsh requirement on the Q distribution. Because if you find some reasonable enough Q, you will converge to that log marginal. Does it make sense? This figure aligned with the graph. Any question? Cool. Yeah, I just want to continue the second part, which I'll try to do that fast. Okay, hopefully I convince you that the new BIS method would be a better fit, especially for POMHP. I mean, it's not really designed for POMHP. Actually, we're working on to show that the generalizability of such a variational inference to many more difficult approximate modeling, but we motivate the thing from POMHP. And now back to the POMHP. The Q distribution choice is non-trivial, as I mentioned earlier. Although we can relax the stress of choosing a perfect Q because we're not maximizing elbow, but still Q can be too bad because you still need to use Q as the proposal distribution for the important sampling. So how are we going to do that? Previous choice of Q distribution would be something we call that forward self, where you consider the influence from the history observation X and also the history hidden Z. Right? So you have the history dependence. The thing is, such a method is very insufficient in terms of sampling because you have to sample Z1 in order to sample Z2 in order to sample Z3. That's very inefficient. The accuracy is reasonable. It's not too good, which I will explain why that's the case. And then one thing you can do is you can drop the history dependence to improve the efficient sampling. right? Now it's D only depends on the data, not depends on the history, so everything can be sampled in a parallel way. But still the low accuracy of the approximation because the Q actually drop a lot of dependence information. And what we propose is, what if we introduce some backward information that really tell you how the hidden nodes influence the future visible nodes. So this is similar to a hidden Markov model. In order to calculate the posterior of the hidden, given the whole sequence observation, you need to calculate a forward message passing and backward message passing. So that's similar motivation. And we argue that it's still efficient in some sampling because Z are parallel to each other, but the accuracy is improved by introducing the backward information. So here is just 2 examples to show why it's the case. So this is the x-axis, which is time. The y-axis is the log of the posterior. The black dot is the truth because we generate the data. And the 2 vertical lines are the 2 events we observe. So these are x1 and x2, you can think. And let's look at this area. So the posterior of Z in this area is high because not only something happens here, but also something happens here. So we have to reason to guess that there is an event happening here, might be some hidden neurons happening here that trigger the events here. That's why the likelihood of this hidden neuron is high in this area. This is, but if you use the forward self or the forward, which only consider the influence from history, their posterior in this area will be low. Because they don't know what happens in the future. They only know something happens here and the probability will drop as time goes by, right? But introducing the backward, the red curve now has a rising probability because of the influence from the future events.
Aren't we using, so there is something that we want to be able to predict, but we are using that to predict what's going to happen?
This is not prediction. This is, we already observed the whole sequence. Then what's the probability of the hidden state? That's like what people call smoothing, I think. So like you already have the whole, I mean, I don't know, like it's hidden, similar to the hidden Markov model. It's not doing prediction. Like if I know sequence after this, what's the likelihood of this? It's actually seeing the whole sequence. What's the likelihood of that?
So we are not so much interested in the dynamics. We are more interested
No,
in the...
no, not dynamic. No, this is not a dynamic part. Yeah. Okay, anyway, finally we apply this model. Actually, we have the new inference method, which is VIS. VI is variational inference as important sampling, and VISKL is actually using important sampling, but instead of minimizing chi-square, we are minimizing KL. And we show like on this particular retina ganglion cell data sets, the red bar, which is forward, backward with a better approximate inference actually get the best likelihood. Okay, the last slide is we want to do a little bit of interpretation. Like in neuroscience, people like interpretation. So rather than just getting a high accuracy bar or likelihood bar, we want to see what is hidden neurons or hidden units really telling us. And the way we inspect that is we look at the connectivity weight, right? It's the theta value. So we have rows correspond to a different inference method and columns correspond to a different Q distribution. The top left is the very basic baseline, and the bottom right is our method. So, okay, the interpretation of this matrix is it's a square matrix. Rows or columns correspond to, so these rows correspond to off cells and these rows correspond to on cells, and the last row will correspond to the one hidden unit. We have 16 off cells and 10 on cells. Therefore, if you look at the last column, this last column tells you what's the influence of the hidden unit over the 27 visible neurons. And here we see that actually this hidden unit is saying, oh, it's inhibiting these on cells, but exciting these off cells. So we're not really discovering a physical neuron. the hidden unit actually aggregates some abstract information about these visible neurons. And this abstract information is like the type, neuron type. Remember, when we feed the model, we don't know the types. We only see those like spikes. So we kind of infer this clustering information from this hidden unit. But you don't see anything like that in the very basic model. So that implies the inference makes sense and discovers some interesting parameters. Okay, so that's it. That's basically the end of the last part. So we propose this better inference method with tighter lower bound, and then we propose a better variational distribution family with efficient parallel sampling, especially for the POMHP method. And with that, I want to finish the talk, probably 2 minutes past 1. And yeah, thanks for the collaborators and students in my lab. And I'm still happy and open to take questions.